Welcome to the Apache Sedona Community Office Hour on May this year. Let's get started. So as usual, I'm gonna first introduce a little bit about Sedona, then we're gonna talk about the latest features in the new release and also the features in the upcoming release. For first of all, for people who joined Office Hour for the first time, Sedona is an open source classical computing engine for processing large-scale geospatial data. So Sedona is a top-level Apache project. We have website sedona.apache.org. We also have our GitHub. It is under the Apache organization. We also have our Twitter account. You can find us on Twitter, Apache Sedona. And we also have our LinkedIn account, also named Apache Sedona. We oftentimes post interesting small tips and short tutorials on our LinkedIn account. Be sure to follow us on LinkedIn to learn the latest news and the tips about how to use Sedona. The status of Sedona. So many companies are using Sedona in production. So there are many logos here. So Sedona is a project we started in 2015. It became mature in 2017 and joined the Apache Software Foundation in 2020 and eventually became a top-level project. Sedona have over 10,000 users, and right now I think it has 136 contributors on GitHub and over 2,000 stars on GitHub, over 2 million downloads per month, and its overall downloads actually have exceeded 45 millions. So it also ranked among top 3% most downloaded package on PyFlink. So many people use Sedona in production. Great. Here is a brief overview about Sedona's system architecture. So as you can see from the diagram on the right, Sedona has multiple layers. So the layer on top is the spatial query processing layer. Spatial query processing layer, first it provides spatial SQL, Python, Scala, and Java API. It actually connects Sedona to the broader ecosystem. You can use Sedona to connect to different developer tools, including Zeppelin Tableau, Jupyter Notebook, GeoPandas, and RStudio, which is pretty cool. Sedona spatial query processing layer also comes with several distributed query algorithms, including range query, nearest neighbor query, spatial join query, and also statistic functions. Sedona has a query optimizer that takes this kind of spatial SQL queries and automatically decide which query is the best for this, which algorithm is the best for this query, and then it's gonna distribute the query to hundreds of machines in the cluster. The second layer is called distributed spatial dataset layer. So this layer actually has powerful features that decides the data layout within the cluster. That includes spatial data partitioning, spatial indexing, and the spatial serialization, so on and so forth. You can also use Sedona on top of for batch data processing as well as stream data processing. Sedona can run on top of a few distributed engines that includes Apache Spark for batch data processing, Apache Flink for streaming data processing, as well as Snowflake. On Snowflake, we have a Sedona plugin called Sedona Snow. You can find it on Snowflake native app marketplace. And Sedona can read many different spatial data formats, including shapefile, GeoJSON, Parquet, GeoParquet, HDF, GeoTIFF, so on and so forth, and it can connect to multiple different data storage. And the easiest way to get started with Sedona is to Sedona Docker image. And we have official Sedona Docker account on Docker Hub. You can find us there. And the easiest way to do that is you can pull the latest Sedona Docker image 171, and you can run this Docker image like this, right? So what this gives you is a Jupyter notebook that allows you to run some Python examples, which is pretty cool. It also can show you a Spark cluster that has a single worker and a single master. And Sedona follows the 3-month release cadence. So we made a couple release last year, and the last release we made was in March this year. 171 we made in March on March 13th, 16th, and we plan to make another release around in June this year. And one important thing for this release, we're gonna target 180, but this release is gonna have several big breaking changes. In particular, I'm gonna talk about that later. It will introduce Java 11 support and drop the Java 8 support, meaning that you won't be able to run Sedona on any Java 8 based runtime environment on the cloud. So because of that, we plan to release another version, 172. So 172 is going to be the last release on Java 8. It will only include bug fixes. So there were a few bugs we discovered after release 171. So we want to provide a few bug fixes so that you can still safely run Sedona on Java 8 environment. So what's new in 171 release? So 171 was made in March this year. Couple interesting features there. First of all, it has the SQL interface for our geostatistic toolbox. So in Sedona 170, we introduced a few cool spatial statistic functions, including dbScan, getIsOr for spatial hotspot detection, and the local outlier for outlier detection. And in Sedona 171 release, we also introduced the SQL interface for the 3 functions here. So you'll be able to run them directly from SQL. Another interesting feature is the broadcast k-nearest neighbor join, so that if you have a k-nearest neighbor join, so k-nearest neighbor join was an algorithm we introduced once in 170, and in 171 we introduced a broadcast join algorithm to further speed up query. And by the way, so we also realized there was a performance bug in broadcast k-nearest join in 171. We already fixed that. We plan to release the performance bug fix in Sedona 172. And STAC catalog reader is another cool feature. I'm going to talk about that later. And the OSM PBF reader, you'll be able to directly read PBF files from the OSM dataset, and it will give you node, weight, and relation. And the spatial partitioned data frame for GeoParquet files. In this release, we introduced a better way to generate balanced GeoParquet files that gives you very tight GeoParquet files in the sense that so each GeoParquet file has a very tight bounding box, so that you will do filter pushdown on those GeoParquet files. You have really good filter pushdown performance. And for new ST functions, another interesting feature is now you can actually convert Sedona data frame to a GeoPandas data frame through GeoArrow, which roughly speed up the process by 2x. All right, now let's delve deep to a few features we released in 171. So an important one is the GeoParquet with balanced partitioning, right? So as you know, Sedona is really good at partition spatial data based on their spatial proximity, such that each partition in a Sedona data frame has roughly same physical size, but also the data in each partition are still neighbor, still spatially close. So this feature could actually help the user to generate really good GeoParquet files, such that each Parquet files have a really tight bounding box for filter pushdown. So in Sedona release 171, we actually expose this function as a external function. Expose this partition method as external functions to the users. So you can actually use something called structure adapter we introduced in 171 that convert a data frame to a special RDD. And then you call our internal API, special RDD dot special partitioning without duplicates. And you can use the KDB tree partitioning in Sedona. And after you partition the special RDD, you can get it back, get the original data frame back. You can have better partitions. And after that, you can directly write this special data frame to GeoPacket files. Use the traditional Sedona GeoPacket writer. This gives you better partitions. You will notice that if you look at the GeoPacket files you write into S3 bucket, you'll notice that each file has roughly similar size, and actually their boundaries are also very tight. And the geo arrow support in Sedona data frame, right? We in 171 we introduced two more functions. So if we want to create a Sedona data frame from a GeoPandas data frame, you can use this specific function called create spatial data frame. You can import this one from Sedona geo arrow utils. It will give you a Sedona data frame through geo arrow conversion. And similarly, once you have a Sedona data frame, you want to get a GeoPandas data frame, you can also use this thing called data frame to arrow. You can import it from Sedona.spark, and you can convert that to a GeoPandas data frame. And it is 2x faster than before. And another interesting function is in 171 is called is faster rasterization. So there are a couple raster functions in Sedona actually rasterize the geometries and overlay them or aggregate this geometries together with pixels to give you some sort of like analysis results. So this includes a function called RS as raster, and also includes function like RS to know statistics, RS to know statistics are. So those functions are widely used by our users of Sedona. So one key operators in these functions is rasterize. So as you see here, it takes a polygon geometry as the input, and it tries to basically convert this polygon to a raster image. To a raster image given the input width and height of the raster image. So what you get is something like this, right? So as you see here, this VR polygons was a geometry. Now we're able to convert them to raster geometries. And usually we can use this shape here. We can aggregate the pixels within the shapes here. You can actually calculate, for example, pseudo statistics. So what is the average value of the spatial observations within this region? And in Sedona 171, they also fixed the performance issue in this rasterization. So now I believe it is at least a couple times faster than before. All right. Another interesting feature is stack reader. So I believe you guys, if you have experience with raster data before, so you probably know that. So stack catalog is a very, very popular way for people to host raster images. And oftentimes, if you want to download some raster images, you oftentimes need to connect to a stack catalog, and then you're going to export data there and download data you want. So stack is a really complicated structure, but long story short, think of stack as a tree structure, and each node of this tree is a GeoJSON file. And the leaf nodes, all the leaf nodes of this tree, they are assets. So the assets in this case, they are actually images. So searching a stack catalog is very similar to searching a tree. You start from the root. The root is a GeoJSON file, and you based on the search criteria, you actually go down to different branches, and eventually once you reach the leaf nodes, you return the leaf nodes to the as a query result. So those are the for example, raster images or geotip files that are within the region you are interested, right? So this is a search of stack catalog. So in Sedona, we introduce a native stack reader. It actually will perform the tree traversal itself, and given search criteria, it's gonna gives you the data that fall in the query window. The way to do that is actually very simple. You can use sedona.read.format, and you can put URL here. So URL here is actually a URL of a stack endpoint, right? This one is actually from element 84. Pretty cool. And you can also do that through a SQL query. So select from where, and interestingly, in the where clause, you can actually put a special predicate there, st contains. So this means you only want to find the raster images that are within this polygon, right? You can run this query after the this read statement. So Sedona actually will perform a filter push down the query filter to the data source, to the stack endpoint. It will only find the result that is within the st contains window, which is pretty efficient. And the result in this example is going to be a data frame, as you can see here. So this data frame is a result of our stack catalog assets. So it is a very wide table, has many columns, but basically you have bounding box, so that's a geometry, also a polygon, right? And also the I think the assets is right here, right? The assets contains a bunch of URL that actually points to the raster images itself. You can actually use this data frame and you can join that with another data frame, Sedona data frame. You can basically perform like a vector raster join based on that, which is pretty cool. Okay, so what's new in the upcoming release, Sedona 1.80? Sedona 1.80 will be released next month. So we are looking at a few exciting new features here. So first of all, Java 11 support. I think this is probably the most important thing in the next release because it's gonna affect many downstream users. Another one is the Spark 4.0 support. Spark 4.0 probably going to be out in a month also. So we already have an ongoing PR to test Sedona compatibility with Spark 4.0. So please stay tuned. Once Spark 4.0 is officially released, so we will be released support at the same time. Another feature is PyFlink support. And as I mentioned before, we will also make a Sedona 1.7.2 release just for bug fixes and for supporting customers that are still on Java 8. So now let's talk about why Java 11 support is important. This is actually related to many issues we have in Sedona in the past. So this allow us to use the latest versions of the underlying dependencies. We have been attempting to use Java 11 last year, but we eventually decided to reverse that change because we noticed that there are many users are still on Java 8, and the cloud, the majority, like half at that point last year, so I think half of the cloud hosting services are still on Java 8, which is not good. But anyway, so this allows us to use lots of cool the latest underlying dependencies. So for example, this allows us to use GeoTools newer than 28, version 28. And this allows us to integrate with Apache SAS. And Apache SAS is an Apache project that is designed for raster data processing. It has many cool functions. and it is well maintained and more advanced than GeoTools in many cases. So we want to integrate with Apache SAS, and this also allows us to have like to allow GeoTools and Apache SAS coexist in the same project. And all these dependencies, they rely on Java 11. So we have to upgrade to Java 11 for that. And another interesting thing is Sedona Snow, which is the special plugin for Snowflake. It must use GeoTools newer than 28. This is because there is a CVE issue, and this was reported last year, and this has been fixed in all GeoTools versions other than GeoTools on Java 8, which includes GeoTools 28. GeoTools 28 is a Java 8 version, and the fix was not ported to GeoTools 28. This means this bug still exists in Sedona Snow currently, and is GeoTools 28 currently, and we won't be able to release new Sedona Snow versions to Snowflake because Snowflake automatically reject all new Sedona Snow versions that has this CVE. But if we use Java 11, we will be able to use the latest version of GeoTools, so we can get rid of this issue. All right. And what's the impact? How that's going to affect our users? So based on the survey we did recently, so now all major Spark hosting services have at least one long-term LTS, long-term support version on Java 11. So here is the survey we did. On Databricks runtime 16.4 LTS, it now defaults to Java 17. And the AWS Glue 5.0, so which was released last year, December last year, it defaults to Java 17. AWS EMR has been supporting Java 17 long time ago. You can use a like newest EMR version like 7.x. So it will default to Java 17. And the Microsoft Fabric have been supporting Java 11 long time ago. You can use Java 11 by default on Microsoft Fabric starting from version 1.2. And the Google Data Prep Spark, right? So that one has been supporting Java 11 long time ago from version 1.0. So as you'll see here, I think I probably covered almost all major Spark hosting services, and they all have a Java 11 LTS version. So I think at this point, it is safe for us to migrate to Java 11. And as a user, so once we release Sedona 1.8, you should pay attention to this one, and you should be sure to upgrade your runtime version to a version that defaults to Java 11 plus. And the Snowflake Java UDF have been using Java 11 a few years ago, so which is safe. So we can easily use Java 11 there. And the Flink, Flink 2.0 has been released, I think a few months back. Flink 2.0 defaults to Java 11, so which is great. So I don't think we're gonna have a problem with Flink as well. Cool, that's Java 11 support. And in this release, we will also introduce PyFlink support. So Sedona has been supporting Flink a long time ago, but it is mostly from the SQL environment or Java environment. So recently, PyFlink has gained lots of traction. More and more people start to pay attention to PyFlink and use Flink through Python. And now we are working on PyFlink support. The PR is almost there. It is already created, but we are still working on that, but it's almost there. And now if you do special queries in PyFlink, you will be able to create a set of context directly in Python. And then you can run a SQL query like this one, right? So like select ST area from a buffer area in a special set of special tables. And yeah, so you call that through Python. All right. So another interesting topic Today we have a demo from a Sedona community member, Matthew Powers. So he's gonna show us how can you use Sedona together with Overture data. So welcome, Matthew. Let me promote you to panelist so you can present. All right, Matthew, please feel free to take over.
Hello, everybody. How's it going? I'm gonna share my screen. Sure. All right. Let's present here. Okay, so oh, show. We're going to be chatting about the Sedona query engine and the Overture data in this little slideshow here. So what's Overture for? So Overture is powering the next generation of map products. It's great for geospatial developers, and that's why we're diving into it. So Overture allows for collaborative map building, which is really cool. So it's basically like a bunch of different organizations are collaborating on the data side of things and also on the code side of things. So everybody's collaborating, putting their best map data together, and then giving the community these like amazing maps for free. They're working on this global entity reference system, the GERS ID, which is giving these unique IDs to all of the objects in the maps. So like there's going to be an ID for a building, which is great. That's actually a very hard problem, as anybody who has experience building maps knows. Overture also has an extensive QA process that's doing extensive checks to make sure that the data is good in the data sets that are released, and they have a great schema for the different tables that we'll be diving into. So if you've never used the Overture Maps data before, I recommend going to their website and checking out the Explorer tool. This like lets you really kind of look through the data. Of course, here's Manhattan, and there's like Paris roads and world land cover, and like this is like a great tool to like better understand the type of data that's included in the Overture data sets. So let's look at exploring a couple of these data sets with Sedona. So here are the Overture tables. Let's take a quick high-level look at what we have. We have addresses, some base infrastructure, land and water. There's information on buildings, divisions, geocodes, places, and then transportation infrastructure. So in order to get started with just like exploring this data, what we're going to do is just run some queries and see what kind of interesting analyses we can perform using Sedona and the Overture Maps data. So in this case, what we're going to do is grab all of the buildings in downtown Los Angeles. So we're going to select all from buildings. The buildings is, of course, the buildings table as defined in the Overture dataset. And then we're just grabbing all the buildings that are in this downtown LA polygon. We're looking just for the buildings in downtown LA. And we're trying to figure out all the buildings that have a height that's populated, and we're ordering by height descending to grab the 20 largest buildings. So we grab those 20 largest buildings. And of course, Sedona is, as a distributed query engine, is really good at these sort of spatial filtering operations. And then what we want to do is create a deck visualization. We can just use the Sedona PyDeck to build this map. So we create the geometry map, and we have this really nice PyDeck visualization of our data of the largest buildings in LA. Let's look at another question we can ask of the data. Now, this one was kind of really interesting for me in particular. I'm from New York, and what I was looking for was like how many pools are in New York City. So in this case, I just drew a little polygon to represent Manhattan, the Bronx, Queens, and Brooklyn. And then I just looked at how many swimming pools there were. This was from the base water view, if you look at the query. And what I had to do is just look at the leisure source tags, which were swimming pools. And then we're again doing that spatial filtering, just looking for all of the swimming pools in that New York City polygon. And in this case, instead of using DEC, we're using Kepler to build this visualization. We have this Sedona Kepler, which is just kind of built in and gives you these visualization tools for free. And we instantiate the Sedona Kepler map and just add our little data frame with our data. And we can see how many pools there are in New York City. There's actually over 20,000. We could kind of see some neighborhoods in kind of Queens and Brooklyn that are almost everybody has a swimming pool. So this was quite a surprising little visualization for me. Again, this isn't probably something you're going to want to do in your production analyses, just kind of showing these little examples so folks can get a feel of what's in this data and also like how easy it is to query with Sedona. Cool. Let's perform a little bit of a different analysis here. Let's find out all of the dance schools in Bangalore and then convert this to a GeoPandas data frame. So here we have a Bengaluru polygon. In this case, we're going to hit the places data set, and we're looking for all of the categories.primary where it equals dance school. And we're finding, of course, doing the spatial filtering, finding all the dance schools in Bengaluru. So the places data set is kind of huge. And for these huge spatial filtering operations, Sedona is a very good query engine. But once we kind of grab the dance schools, let's say there's only like 1,500 dance schools, that's a data set size that's significantly smaller and can comfortably be converted to GeoPandas. Now, of course, you don't need to convert it to GeoPandas, but let's say in this case you want to do something GeoPandas E with it. So we'll just see how to do this. So all you have to do to convert a Sedona data frame to GeoPandas, you just take the pandas data frame. We can instantiate that to pandas method. That creates pandas data frame, and then you can use that pandas data frame to create the GeoPandas data frame. And we can see it's very easy to look at the data in GeoPandas. After converting it, we can see the geometry, the name, and the phone number of these Bengaluru dance studios. Okay, cool. So you might wonder, why does the Overture Maps Foundation distribute their data as GeoParquet? So I wanted to give a little demo here that shows like the data in GeoJSON, run a query, see how slow it is, and kind of highlight why having the data in GeoParquet is so useful. So what I did here was I took the buildings data set and I wrote out 4 columns to GeoJSON files. And in this case, this polygon is just a little polygon in like rural Florida. And what we're doing is we're just looking how many buildings are in this little rural polygon. I think the buildings data set has around like 2.6 billion rows of data. In this case, this little polygon just has like, let's say 2,000 buildings, a very small amount of buildings. So if this data is stored in GeoJSON files, we can see that this query, just to grab the number of buildings in this small polygon in Florida, it actually takes 47 minutes to execute. So that kind of like takes forever. Now, if this data is stored in GeoParquet files, which is what the Overture Maps Foundation stores their data in, we can see that the same query only takes 48 seconds to execute. Now, the reason it's so much faster is because GeoParquet file are first much more efficient. They store their data in a binary format, but also there's a bunch of query predicate pushdown filtering that the Sedona engine can leverage to make this query run much faster. So that's kind of just a motivating slide to explain why we like GeoParquet a lot. Cool. Let's take a look at just a couple more things we can do with this data before wrapping this up. This is an easy way to kind of read in the buildings data set into the buildings data frame. And here's how we can see it has around 2.6 billion rows of data. One thing you can do, this is just a partial dump of the schema, but you can run print schema to see the schema of all these individual tables. Definitely recommend like digging into all these tables, checking out their schema, checking out the values, and then figuring out like how you can use this data to augment your analyses. Let's just look at a few rows of data here. We are selecting the ID geometry, height, and number of floors, and just looking at 5 rows of data here. So pretty cool stuff. And let's just finalize with this WKT library that I'm building based on this Overture data. So in this case, what I've been doing is trying to figure out an easy way to get WKT for all these different regions. As you can see, I'm like hard coding it, some of those examples. And then I had a colleague who was mentioning that it's much easier to just grab this well-known text directly from the Overture data. So I created this little helper method using this division area data set and just grabbing the WKT for different countries and counties and cities. In this case, this is how to get the WKT for the United States. But there's another thing that the Overture dataset is great at. If you ever want to just grab WKT, you can just query this division area table. So hope you have fun diving into this Overture data. It's like very rich data set and tons of cool analyses can be done there. So I'm looking forward to digging into it more and highly recommend doing it with Sedona because the distributed nature really gives you a performant way to run the queries. I'll pass it back to you, Gia.
Thank you, Matthew. All right. Oh, thanks for the demo from Matthew. And as always, Sedona is calling for help. So there are many ways that you can help the Sedona community. For example, you can contribute notebook examples to Sedona, and that help us to about users to know how to get started with Sedona. We also have our documentation website, right? Please feel free to contribute more tutorials and also fix typos in the website. And we also make release tests, so meaning that before we release a Sedona binary to production, so we always perform several rounds of tests on the release candidates. So you can help us by verifying the release candidates before it's actually released. And then you can help us verify if there's any bugs or help us verify signatures and some basic correctness test. And we also do periodically do some live stream about Sedona success story, about how you use Sedona in your environment and how Sedona helps you make sense of your data. So if you're interested, please contact me. Right. Also, you can reach out to me through Sedona Discord. And my email address is jayu@apache.org. You can reach out to me there. Oh, yeah, I think that's all I want to present today. Now I'll leave some time to you guys so you can raise your hand and ask questions. Oh, I saw you raise your hand. Now you can speak, please.
Hi, Gia. Hi. I just had a quick question with respect to your product roadmap and really just wanted to understand your thoughts. I noticed that several people mentioned NVIDIA Rapids around the discussion that you made at CNG, and I wasn't really sure what you thought of it. I was just wondering if you could share your thoughts on performance in some of the image machine learning tasks or other areas that you think that might eventually come into play or not. Be greatly appreciated. Whatever you're willing to share or can share.
Oh, yeah, great question. So, as you mentioned, so NVIDIA Rapids is a great tool for people to perform data to accelerate data processing through GPU, which is great. And NVIDIA Rapids actually also have a Spark plugin that actually allows you to accelerate Spark data processing through Rapids. This is great, and if you, actually that works with Sedona actually. So if you want to try it out, you can actually try it out on like uh, probably AWS EMR. So you can put uh, Spark Rapids in there, and it will work together with Sedona. Of course, it will only accelerate regular data processing. now the spatial part. So regarding the accelerating spatial data processing through GPU, so I think that's a great idea, but there are a couple challenges here. So there is a project called Q Spatial already there. But the problem is this approach is that so the basic idea here is when they do geospatial data processing on GPU, they rasterize the geometries. So say if you have a polygon, right? You rasterize the polygon to a bunch of pixels and you send all the pixels to the GPU. And of course, if you do like a pointing polygon check, you need to rasterize both sides. You need to send that to GPU and perform the data processing here. So let alone if I'm not sure if it will actually accelerate the pointing polygon check or not, but as you can see here, as it basically changed the way you process the spatial relationship, meaning that you are lose accuracy, lose precision, because you are no longer doing pointing polygon, you are doing joins between pixels, right? So that's my understanding. So there's some risk there. So it might not be the best approach for you to do spatial processing on GPU. And another problem is in many spatial data processing queries. So the basic operator is a spatial join. As many of you have been noticed, I guess, like one of the cool features of Sedona is a spatial join, right? So spatial join is very it requires huge data shuffle. You need to shuffle data across the network, and in that case, this query is actually I/O bounded. It is no longer compute bounded. So GPU will only accelerate compute, but as you see here, compute is really not the bottleneck. It's the bottleneck is the network, is the data transfer, right? Meaning that even if you're able to accelerate the spatial data processing query here, still the vast majority of the time is still on transferring data. So you probably won't be able to see lots of performance gain here. So that's my understanding, but we are still like investigating and perform some tests here and there and see if there is a way that we can actually leverage the power of GPU. So yeah, we will keep you guys posted.
Thank you so much.
Hey, Matthew,
Uh,
please.
yeah, I wanted to try out the stack reader, and I was just wondering if there's any like good place there's like a place with an example that I could try it out and like run a real analysis with the raster data.
Yeah, that's a good question. So there are a couple very popular stack catalogs here. So one, as I showed in the presentation today, one is actually from Element 84. So that is one. I think there's another one from probably Planetary Computer or Microsoft. So that has very cool visualization. And I think another popular one is from Reading Earth. Let me see. Yeah, so this is pretty cool. It's a cool. Let me this one. So this is a pretty cool stack browser from Reading Earth. You know the company, the organization behind cloud native geospatial. So it has lots of stack data sets here. You can take one of them and you can look into the data set here, right? It tells you what data set you have and also the region. And please notice that. So this is a stack catalog endpoint. It actually uses a JSON file. So I think you can get the source. Yeah, this is the source of the stack metadata. You can give this to Sedona. Oh, there are many other interesting data sets here, right? You can also take a look.
And you were saying that like Sedona can optimize the query and then like pushes down those filters to like read the minimal amount of rasters.
Yes, it allows you to give a spatial and a temporal extent. So it can give you the data set that fall inside this spatial temporal region. So it does not actually return you the entire data set. It does not load the entire stack catalog into memory or into the memory of the cluster and then perform filter. It actually performs filter before loading the data set. Oh, guys, any questions? Feel free to raise your hand. All right, guys. So if you have no other questions, we can stop here today. As always, if you have any questions, you can reach out to us and on Discord. And by the way, we recently enabled the discussion tab on Sedona GitHub repository. So if you have questions, there are multiple ways to try it out. So this is Sedona GitHub repository, right? You can put questions here on GitHub issues. You can also paste question here. We recently enabled the discussion tab of Sedona, so you'll be able to put question here as well. So there are already a few questions here, but feel free to create new questions. All right, guys. So if you have no other questions, you can stop here. And thanks for attending the office hour today.